In this video, we will go through the integral formula for the surface area setup. So we're going to build that integral formula and then use it. It's not too difficult. It's going to kind of follow from some of the other kinds of methods and formulas that we've already built. So this should seem relatively comfortable if we're familiar and comfortable with being able to find volume using disks and washers and shells, and also understanding how that arc length situation went. So here we go. Like I said, similar to the volume situations, we're going to be revolving around an axis. We're going to go back to our solid of revolution. You'll notice that when we did arc length, we didn't have any revolution around an axis since we were just looking at a one-dimensional measure of length. Here, we're going to consider some function that acts nicely. We'll talk about what that means a little later on this interval from A to B. If we form a solid by revolving around the x-axis, we're going to use that slice and sum strategy, and what's that surface area going to be? So let's just go ahead and draw this out a little bit. I'll draw a nice axis here. Maybe I'll make this a little bit smaller so I have some room for myself later on. So I'll draw my axis over here. Our function is going to be greater than or equal to 0, so we'll just say it looks like this. We're going to have some point A and some point B. We're going to revolve this region here around our axis. And we've seen shapes like this already, and we know that that's going to create some sort of, I'll draw it as best I can, this kind of a vase-like shape. And our question is, how do we find surface area? We're going to use slice and sum for this. So we know we're going to be looking at some sort of a partition and looking at some sort of a cross-sectional piece. Now, with volume, we use just regular rectangle. But then with arc length, we ended up using a straight line approximation here. So that's what I'm going to use. I'm going to use a trapezoid, and I'm going to approximate the line, the curve on that subinterval using a straight line. And so if I do that, what I'm going to get right around here is this little cutout, but it's going to have a straight line here. So it's going to end up looking something like this. This almost looks like a shell, except for us, let me see if I can draw this better. There we go. Oh, that's the wrong way. It's going to go like that. There we go. It's going to be like a cylinder, like one of our shells here, except we're going to have these tapered edges. Really what this is the portion of a cone. And so what we need to do is figure out the surface area of this piece, not a volume anymore. We want the surface area of this little shape here. So to do that, we're going to have to talk a little bit about that shape, see how it goes, and it's going to turn out to be really similar to a cylinder. We're just going to have to be careful about one thing. So that shape is called a frustum, and this is the area formula if you look it up. It's 2 pi times the average radius times the length of that diagonal. So L in this case is this here. And again, this average radius is the average of R1 and R2, where I guess you could say R1 is on one side and R2 is on the other. So we just have these two different radii describing the tapering of this thing, and we have a length in between. So that's what we'll do. You'll notice that if we take this and plug it into our formula, the 2's cancel out, and so we could call it like pi times the sum of the two radii times that length. But what we're going to do is leave it in this form because we can find that average radius pretty easily. Because the line connecting the two radii is diagonal, I shouldn't say the two radii, but the two edges, I'll say, as a diagonal linear line, the average radius is literally right in between. So that ends up being pretty easy. So what we're going to do is leave it this way, and what you'll notice is that we'll just have to be a little clever about how we deal with this. Let me go back and get this picture. I'll put that on this page so we can look at that a little bit. And then I'm going to draw my frustum again. I always have a hard time saying that word, so I'm trying to be really careful to make sure I get it right. All right, cool. So what we're going to do is we're going to pick the average radius to be somewhere right in the middle here. This is going to be our average. And you'll notice that what that means is that that's just right here. And the radius part is the y value, right? It's this distance. So what we can say is that this is going to be our f of x sub k star. X sub k star is going to essentially just be the midpoint, or the x value that will give us the average radius here. Easy enough. So once we've got that, we can set up our area pretty easily. That's going to be 2 pi times f of x k star times the length of that curve. Well, and the nice part is that we've already built the length of that curve. That's the arc length, which we can approximate on that subinterval using a straight line approximation, and it looks like this. Oops, I want my delta x in here. So now notice the delta x part is baked into our arc length. That's the part that's going to have us set this up as a Riemann sum. Couple of things to make note of. Here we said x sub k star was the midpoint, but remember with arc length we said it was the point where the mean value theorem guarantees that that derivative is equal to the slope. Those technically could be different points, right? And so what we have to notice is that if we force these to be the same, it's going to be fine, because when our intervals get closer and closer to each other, or smaller and smaller, I'll say, the little subintervals, as n goes off to infinity, we're going to collapse that choosing point right in the middle, and it's just going to turn into x anyways. So, oops, that's a little too far. So we'll say then our area is approximately the sum of all these things, 2 pi f of x sub k star, that's our radius in this case, times the length, 1 plus the derivative at x sub k star squared under a square root, and then we multiply by delta x, and that means that we can apply a limit as n goes to infinity of this sum from k equals 1 up to n of 2 pi f of x k star times the square root of 1 plus f prime x sub k star, there we go, squared times delta x. Whew, that's a lot of stuff. Notice once we apply that limit, this is going to turn into an integral. Our delta x is going to turn into a dx. This summation notation out front is going to turn into some integral notation, and all of our x sub k stars are going to turn into x's. Here's our integral formula for surface area. Now, we said earlier that f has to be a nice function. Here's what we mean by nice. It's got to be a function that's non-negative. It's going to be continuous, but more importantly, the derivative is going to also be continuous. So not only does our function need to be continuous, it needs to be differentiable. And not only does the derivative need to exist, but the derivative needs to be continuous also on that interval. Then, if you take that region bounded by the graph in the x-axis on the closed interval and you revolve it around the x-axis, there's your surface area formula. 2 pi times your radius times your, and this I remember was the average radius, times your arc length, L. Notice that this is essentially just the area formula for a cylinder, though. It's 2 pi r h, where normally we'd say that h is the height. Well, now what we're doing is we're putting it on its side. And so instead of h for height, we're calling it L. That's essentially what this is. So that's how I always remember it. I never really remember that area formula for a frustum, although it's not hard, because what we're doing with a frustum is you're saying that's going to be the same as the area of a cylinder whose radius is just the average radius of your frustum. So that's really the connection that we have. We just do a little trade-off of the radii to make it look like a cylinder, and bang, there's our cylinder. Just like arc length, this is an ugly integral formula. It's probably a little worse, actually. And so this one, we might not be able to evaluate it that easily. We'll do a couple of examples where we actually can evaluate it, but you'll notice that especially the second example, I think it is, that we look at, it's almost going to seem like a toy example because we have to like force it to work the way that it's going to work. You'll see what I mean when we get there. So let's take a look at these two examples. All right, so here's our first example. We've got this square root function. Maybe I'll just sketch it really quick. Let me do some straight lines on here. None of this messy line stuff. All right, so we've got this square root function between 1 and 3. And we're going to take this region, revolve it around this way, create this nice kind of bowl-looking thing. Oops, I got to cut this off at 1. There we go. Create kind of like a bowl-looking shape. Here we go. That's better. And we want to find the surface area of this. Now, we could find the volume using the disk method, but what we care about is the surface area. I still like to draw in my little trapezoid in this case, but really I like to see it so I know, okay, delta x, I'm leaving everything in terms of x. I know I'm going to need this 2 pi RL, where L is my arc length. That's really going to be a Pythagorean theorem thing that we did last time. So we'll get that. So for the radius, I know that that's going to be the height of my function. So my volume is going to be the integral from 1 to 3 of 2 pi f of x times that square root. Here's my Pythagorean theorem coming in. We've got this slope squared dx. I normally write this with the 2 pi out front, and now I'll put everything in. I'm not leaving myself much room, am I? Let me get a little bit better here. 2 pi times my integral from 1 to 3 of my function, 2 root x, times the square root of 1 plus the derivative squared. The derivative of 2 root x, we can see we'll bring that half out front, and f prime becomes 1 over x to the half, because we'll have a negative half, so I'll call it 1 over root x. And then I have my dx out there. Notice that I'm going to start with this part here, right on the inside. Let's square that. That becomes 1 over x. We don't have to worry about the absolute value because our x values are going from 1 to 3 anyways. I'm also going to take this 2 and just bring it out front. So I've got 4 pi times the integral from 1 to 3 of root x times the square root of 1 plus 1 over x. And now you'll notice that I've got a square root times a square root. I can do some distributive property. And this is 4 pi times the integral from 1 to 3 of the square root of x plus 1 dx. This part should be easy. We should be feeling good. U is equal to x plus 1. du is equal to dx. This is really just a nice little square root thing. So we've got 4 pi integral. My new limits of integration, I'm going to add 1 to these x values to get my corresponding u values. So it's going to go from 2 to 4. And I'm going to have a square root u. I'm going to write it as u to the half du. Anti-differentiate, so it becomes u to the 3 halves. So I've got 4 pi times 2/3 u to the 3 halves evaluated from 2 to 4. Cool. Let's see. So 4 pi times 2/3 is really 8 pi over 3. And then 4 to the 3 halves is really 2 cubed, so that's 8. And 2 to the 3 halves is really the square root of 8. Whatever that is. So you could leave it like that if you wanted. You could multiply it all out. I don't really care. But that's what this looks like. Not too bad, right? Let's take a look at... Oh, I gave myself another slide in case I needed it. I didn't need it this time. Let's take a look at this one. We'll consider the region bounded by this curve and the x-axis between 1 and 2. And we're going to form that nice solid by revolving around the x-axis again and find the surface area. I'm not going to sketch this one because we don't really need to, but we should double check and make sure that this is actually positive. Notice it's a sum of two things, and the x values that we're looking at are both positive, right? X equals 1 up to x equals 2. So if you put positive numbers in here or here and add these things together, you're guaranteed that your function is positive. Okay, whew, good. We also aren't going to have any problems with discontinuity because we're not going to divide by 0 because we'd have to be looking at the x value of 0, and we don't have that in our interval. All right, so we know we need y, but we also need y prime. This is going to be 3x squared minus, you could say this is really 1 over 12 x to the negative 1, and so it's minus 1 over 12 x squared, 1 over 12 x to the negative 2. So that's our derivative. All right, so here's our volume formula. 2 pi times the integral from 1 to 2 of our function, x cubed plus 1 over 12x, times the square root of 1 plus our derivative squared, dx. I will need the second slide for this one. This is the one where I think I said earlier, it's going to seem like this is like a trick, and it kind of is. What you're going to notice is that this function is set up so that nice things happen, because right now, this looks terrible, right? Doesn't this look super ugly? And so we're going to clean this up, and you're going to notice some magic happens, and it just works out really nicely. Cool. That'll be nice. All right, I'm going to start again with squaring the stuff under here. So I've got 2 pi times the integral from 1 to 2 of x cubed plus 1 over 12x. I still have this square root of 1 plus, but now I've got 9x to the 4. Then I've got 3x squared times 1 over 12x squared. That's a quarter. But I'm going to get 2 of them, right? So this is really minus a half, because I got 3x squared times negative 1 over 12x squared, and I've got negative 1 over 12x squared times 3x squared. Then I've got negative 1 over 12x squared, which is 1 over 144 x to the 4. And there's not much to do except this. I can combine these two terms. All right, whoopee. Let's do it. Integral from 1 to 2 multiplied by 2 pi. X cubed plus 1 over 12x. We've got this square root of 9x to the 4. We've got a 1 minus half, so this becomes plus half, plus 1 over 144 x to the 4. Now I want us to pause for a second, and I want us to focus on this. That was really this big thing squared, compared to what we've got here. What's the difference between the last 3 terms here? That was our 3x squared minus 1 over 12x squared, and the 3 terms underneath our square root here. Hopefully you'll notice that it's just the sign that's changing. What that means is that we can factor this, and we can say 9x to the 4 plus a half plus 1 over 144 x to the 4 is really equal to 3x squared plus 1 over 12 x squared squared. If you don't believe me, pause the video and just multiply this out. But you'll notice our first term is a perfect square, our second term is a perfect square, and the middle term is 2 times each of those square roots of that thing. It's got a positive sign here, so we're going to be adding these together. Okay, so what does that mean? That means that we can take that volume integral formula that we had, and we'll say this is from 1 to 2. We still have our function out here. Nothing's happened with this yet. It's pretty boring over here. But now, under our square root, instead of all this garbage, we're going to take 3x squared plus 1 over 12x squared. We have a perfect square polynomial. Hey, look at that. We can deal with this square root. Congratulations, there's the trick. We're going to get rid of this ugliness on our square root with this cool little factoring thing after we combined all that stuff. You're going to see this trick a decent amount in these problems because there aren't a lot of ways that we can get problems set up nicely for us to be able to evaluate them yet otherwise. Now we can multiply everything out. I might even need more slides. Whew. 2 pi times our integral from 1 to 2. And now I've got x cubed times 3x squared. That's 3x to the 5th. I've got, let's see, x cubed times 1 over 12x squared. That's going to be 1 over 12x. Then I've also got 3x squared times, oh, no, sorry. This is x over 12. Whew, that was going to be annoying. So that was my x cubed times 1 over 12x squared. Now I've got 3x squared times 1 over 12. This is 1 over 12x, sorry. This is going to be 3x over 12. So you'll notice I can combine these things to get 4x over 12 or x over 3. And then my last term is 1 over 12x times 1 over 12x squared. This is 1 over 144x cubed. Let me rewrite this out. 2 pi times my integral from 1 to 2 of 3x to the 5th plus 1/3 x plus 144 x to the negative 3 dx. Okay, so now we can antidifferentiate. Ugh, that was annoying, right? 2 pi times, here's our antiderivative, 3x to the 6 over 6, so I'll call that x to the 6 over 2. Then we have a third x squared over 2, so that's x squared over 6. And then we have 144 x to the negative 2 over negative 2. And I'm trying to do arithmetic in my head. Minus, what's this? 72? Yeah. 144 divided by 2 is 72, I think, right? Arithmetic is really hard. That's where we'll get caught. And now you can go ahead and evaluate this. I'm going to leave this for you to finish out because we should be able to just plug and chug through this. Although, like I said, arithmetic is hard. So pull out your calculators if you need them, I guess, and rock through plugging those values in and subtracting. And whatever you get there, that's the surface area. Again, the big trick here is the fact that when you have 1 plus this perfect square under that square root, when you multiply it all out, it turns into another perfect square. So we can deal with that square root pretty well then. Outside of that, there aren't a lot of tricks that we're going to be able to do because, like I said, these get really, really bulky. And so what you'll notice is that for some of these problems, we'll have you set them up and actually evaluate surface area because we can. There'll be some tricks that we can do, or there'll be a small example like this one that we had earlier. But realistically, for a general case, we'll just be setting these things up. And as long as we can understand the setup and explain where the formula comes from, I'm happy. So that's all I've got for this video. That's going to finish things up for these kind of geometrically inspired integral formulas that we've been looking at. And what we're going to move on to is just a couple of little physical applications. These are going to be like the classic engineering examples that all the engineering majors want to see. So we'll talk about some of those really briefly, and that'll be it for this first unit of content.